everybody, this is the second of 7 videos about heaps. So in this video, I'm going to talk about some basic definitions of what a binary heap is and what a complete binary tree is and things like that. So this is just a definitions video. Make sure you understand this terminology because we're going to be using all of this when we look at heaps. And also later on when we start talking about trees, some of these words we're going to introduce now are actually going to be part of the tree section because we're going to be talking about binary trees after we talk about heaps. So let's start with a binary heap. So a binary heap, by definition, is a complete binary tree where heap order property is maintained. So what I want to do now is I first want to go through each of these in turn. So what is a binary tree? First of all, binary trees. Actually, before that, let's talk about trees. Then let's talk about binary trees. And then finally, we will talk about complete binary trees. Now, these things are much easier to talk about through drawing than it is to talk about through writing. So instead of defining everything through like the written word, I'm going to be drawing lots of pictures and then going over each of these in turn. So let's start with the idea of a tree. A tree is a data structure that is made up of nodes that are linked together. Okay, so trees is a data structure where nodes are linked together, Okay, so you have this a bunch of nodes that are linked together, but it's not in a list. Okay, it's not linear in nature. Linked together through more of a parent-child relationship. So we're going to be talking about parents and children and so on. So it's much easier for me to actually draw a picture of this than it is to talk about. So let's talk about what a tree is. So if we were to draw a picture of a tree, you would see trunk, grows up, branches out into leaves, right? Well, trees have sort of the same thing, but we draw it upside down. So our tree is actually going to be drawn the other way. So for every tree, there is a node that we call the root node, root of the tree, which is a node this is the node that begins our tree. So you know how you have the front pointer on a linked list, and that's the first node of the list? Well, the root pointer points to the root of the tree, the node from which all the other nodes are reachable. Okay, so the root node of the tree is the first node in the tree. It's also the node where you can actually reach every other node within the tree. So this is sort of the important part. It's like the first node in the linked list lets you go to all the other nodes. The root node of the tree lets you go to all the other nodes also. Okay. Any way that you implement a tree, no matter how you implement this tree at the end of the day, you have to know where the root is, and you have to be able to find it very quickly. So it has to be like a direct link to it, as opposed to going through like 10 other nodes to find the root. That actually isn't what we do. Okay, so the root of the tree is important. We care about it. Now, for every node, you can have children. So B and C are children of A. So the nodes here that are directly linked with a single link to a node right here, like so. There's one link from A going down to B. So B is a child of A. Similarly, from A, I go down one link, I get to C. C is a child of A. Now, if B and C are children of A, then A is parent of B and C. Okay, so B and C are children. A is the parent of B and C. So if there's a direct link, then you have a parent-child relationship. Now, it is really, really so this is sort of like, like a family tree, right? You have your ancestors, and then, your great grandparents and your grandparents and so on. Same idea, okay? So you have A, B, C. Now, nodes can children can also have their own children. In this case, D and E. They can have multiple. They can also only have one child. Okay. So in this picture, okay, um, actually, let me shrink the picture just a touch. Oops. Okay, so I fit the whole picture in. Okay, so here we go. Um, Now, so A is the root, B and C are children, and so on. Now, any node that has no children are leaf nodes. Okay, so leaf nodes are nodes without children. Okay, so in this case, what are the leaf nodes of this tree? Okay, take a moment, pause the video, identify the leaf nodes in this tree. Go. Okay, so hopefully you have found the leaf nodes, and they are D, G, H, I, and F. Okay, those are the leaf nodes in this tree. So D, G, H, I, and F are leaf nodes in this case. You can have more than one leaf node, obviously. Okay, note that C is not a leaf node, even though it only has one children. So if it has even one child, it's not a leaf node. Okay, leaf nodes have 0 children. Okay. Now, there's a few other terminology that you should know about. So we're going to define them as we go. So I'm going to copy this picture. Okay, just so that I have a bit more writing surface here. So here's the picture. Now, in this case, we talk about each node as existing at different levels. Okay, so what does that mean? It basically means distance from the root. So we talk about the depth of a node. Now, this is really, really important. There's two terms that are always mixed up, depth and height, and they are not the same thing. So depth of a node. So first of all, depth refers to one node, not the entire tree, not a subtree. It refers to a single node, okay? Depth of a node, okay, is the distance from root of the node. So what do I mean by this? Okay, so if we take a look at this drawing, what I've done is I've sort of like uh, marked some dotted lines across this tree. And we can say that this is basically level 0. Okay, this is level 1. This is level 2. This is level 3. Okay, so if we think about this as how many nodes away from the root a node is, if you are the root, you're on level 0. It's 0 nodes away from the root. If it's B, for example, over here, B is 1 node away from the root. D, E, and F, these three, these are 2 nodes away from the root A. These guys are 3 nodes away from A. So if I have to go 1, 2, 3 before I get to the root. Okay, so from G, go 1 node, go 2 nodes, go 3 nodes. That's how I get to A. So that's sort of the difference in this is the depth. Now that idea, the depth of a node, okay? So for example, G is at depth 3, okay? D is at depth 2. So really important is how deep in the tree you are. Okay, how far down do you have to go? Now, this terminology is often confused with another one called height. Height refers to how many nodes there are from the root to the farthest away leaf. Okay, so the farthest away leaves on this particular tree are down here, right? And the root is over there. So if I count how many nodes there are, okay, the height of the tree is defined as here's one node, here, oops, sorry, one node, two node, three node, four nodes. So the height of the tree is 4. There are 4 nodes from the beginning to the end. Now, some textbooks do use, instead of nodes, they use number of branches. We don't do that here. We use the number of nodes. So just count root to farthest away leaf. There's 4 of them right here. Okay? So so this is how you count. Okay? So far so good, hopefully. So this is the depth of a node is the distance from the root. The height of a tree is the total number of nodes from root all the way to its farthest leaf. Now, let's paste another copy of this tree and continue on. Oops. So here is the tree. Okay, this is the tree that we were working with at the beginning. Now, sometimes we create we talk about things that are called subtrees. Now, a subtree is identified by its root. So when we talk about subtrees, we identify the root of the subtree we identify the entire subtree as a root. So what do I mean by this? So for example, if I were to take a look at this diagram and let me very quickly erase some of the highlighting here. Oops. Okay. So if I were to if I was to look at this tree and I talk about subtrees, for example, I can talk about here. Let me use this to say, okay, so this right here, this whole thing, this is the subtree with root C. So basically we view a subtree as a piece of the tree and it starts at a certain point and continues on. So think of it this way. If you have like a real tree and you cut off a branch of it, it kind of looks like a tree too, but it starts at a different place, right? So same idea. Okay, we have the root of the subtree followed by the leaves and so on coming out from that subtree. Now over here, right here, this part, this is actually another subtree. Who can tell me? Sorry, habit. So right now, tell me what is the root of this subtree that I kind of circled in purple? What is the root of the subtree that I just circled? Okay, pause the video. So this is a subtree. Oops. This is a subtree with root of B. So B is the root of the subtree that I've circled here in purple. Okay, so this thing is so that's what we talk about. Now, this is where this gets kind of interesting. So let me copy this over here, okay? And where some of the confusion often lies. So if we take a look at the subtree over here, okay, what is the depth? So very quick quiz, depth of B, height of subtree B with B root. So very quickly tell me what the answer for this is. What is the depth of node B? Okay. What is the height of the subtree whose root is B? Okay, pause the video, answer this question. Okay, so the depth of B is where it is relative to A. So remember that depth is how deep in the tree is this thing. So how far away is B to A? So B is right here, okay? It is one node away from B, or sorry, from A. So the depth of B is 1 because it is one node away from the A. The height of the subtree B, however, this tree has a height that is measured from the root to its farthest away leaf. So B is the root of the tree, is the root of the subtree, and its farthest away leaf is G, H, and I, right? Those are equally far, and they're the farthest away. And if I count how many nodes there is a total of 1, 2, 3 nodes. So the height of the entire subtree is 3. So this is a really, really important concept and really important difference. The depth of a node versus the height of a tree whose root is a certain node. You count different ways. So make sure you don't get the two of these mixed up because they actually have very different meanings. Okay. So that, in a nutshell, is what trees are. Okay, trees are these data structures that have nodes, these parent-child relationships. Okay, there are other terminology that I will talk about when we actually talk more about binary trees, but these are the ones that are important for heaps. Okay, so keep this in mind: height, depth, leaves, and so on. One very important note: trees are completely acyclic. So what it means is that if I have a root node A like this, and then I have B and C like so, if I have this right here, this is not a tree because we now have something called a cycle. We have a node cannot have two parents. It's actually as simple as that. A node cannot have two parents. There's only one parent to a node. So this is not a tree. This is also not a tree. There's no cycles here, okay? But this is still not a tree because I have a node with two parents. Node with two parents, not a tree, okay? So you have to be sort of careful about this in that when you talk about trees, they don't have every node only has one parent. If any node has more than one parent, it's not a tree. D has two parents, not a tree, right? So now we have to talk about trees as this data structure where you have this parent-child relationship, but there's only, for every node, there's only one parent. Parents can have multiple children, but every node can only have one parent, okay? Um, so that covers what trees are, but that doesn't finish our definition. So what about binary trees? Well, binary trees are, well, first of all, they are trees. Trees where each node can have at most, okay, so it's not at least, it's at most two children, okay? You cannot have three children in a tree. So if we look back at our tree, the drawing that we've been looking at, this tree right here, oops, Actually, it's not pasted there. Let's paste it here. So if we look at our tree right here, this tree, this is not a binary tree. Why is that? Well, because E has 3 children. So a binary tree is a tree where, oops, sorry, I just realized it's covered. So this particular picture, this is not a binary tree. Why? Because this E node right here has 3 children. G, H, and I are children of E. So over here, E node has 3 children. This is why this is not a binary tree. This is just a regular tree. So a binary tree is a tree where every node has at most 2 children. It is allowed to have no children. It is allowed to have 1 child. It is not allowed to have 3 children or more. So let me draw some pictures, and you can tell me which of these are binary trees, okay? So tell me if each of these are binary trees or not. Okay, so here's 2 pictures, and let's draw a few more. Okay, so binary tree or not binary tree, pause the video now and write down your answers for each of your trees, and then I will reveal them in 5 seconds. Okay, so first picture, this one. This is a binary tree. If I look at every single node, none of these have more than 2 children. So this is a binary tree. So binary tree. What about this one? The second one. This is not a binary tree because this particular thing has, this node right here has 3 children. So it's not a binary tree because there are 3 children on that node. This one doesn't look like a tree, but it is. It is a binary tree where it's very skewed to one side, but it's still actually a tree. Okay, just because I don't have it's a tree that somebody like was overzealous in pruning, but it is still a tree. Okay, this one is also a binary tree. Okay, so each of these are binary trees except for this one, which is not a binary tree. That's it. So that is the definition of binary tree. Binary tree is any tree where for every single node there is at most 2 children. One last word, complete. Okay? Complete binary trees are binary trees where nodes on one, where every node on one level must exist before any nodes can be added to the next level. And nodes have to be added from left to right. So what does that actually mean for our trees? What do we mean by adding something from left to right? Okay, so let's take a look at this. So first of all, we have our tree over here. So the easiest way to think about this is what our tree potentially looks like. Okay, so if we have a tree, we know that there is always a root node, right? And because it's a binary tree, we know that the root node can have 1 or 2 children. So these are nodes that potentially can exist, okay? So a binary tree with two nodes, a regular binary tree can look like this, or it can look like this if it has two nodes, okay? So binary trees with two nodes. It can look like either or, okay? But if it's complete, it has to look like this, okay? Why? So this is a complete binary tree with two nodes. We have to create the second node, okay? This node must be created before this node. Okay, so if we look at all the nodes across the level, across the same level, we have to fill them, we have to create them from left to right. And we have to create every single node on a certain level before we can create nodes on the next level. So it's a restriction on the shape. So another way to think about this, so let's take a look at a binary tree that has three nodes. Now, if we talk about a regular binary tree with three nodes, there are actually lots of possibilities. 1, 2, 3, obvious, right? Here's a binary tree with three nodes. We can have 1, 2, 3. That's another binary tree with three nodes. Remember, this is the one where, someone got overzealous in their pruning. 1, 2, 3, that's another possibility. 1, 2, 3, that's another possibility. 1, 2, 3, that's another possibility. So there's all of these different ways that we could have configured to get trees, binary trees that have three nodes. All of these are binary trees with three nodes. Okay? All valid three-node binary trees. Okay? Basically, once you've created the first node, you now have potentially two possibilities, right? You have two potential places for the next node. After you fill in the second node, you now actually have, you actually add two more possible locations for the third node, right? So I could either add it here, or here, here, or here, or here. So after I get two nodes, I can add the third one in any one of those positions to get the third node. Now, with a complete binary tree, though, I have to make every single node on any level exist before any node can exist on the next level. So what that means is that because this is the second level, I have to have two nodes in this level completed before I can add these guys. So before I can add this one and this one, I first have to add anything that is missing on this node, and I have to go from left to right. So for three nodes, this is the only, this tree right here with these three nodes, this is a three node complete binary tree. So it's a very strict definition. Three node complete binary tree is this thing. This is three nodes and complete. Now, if we keep looking at it like this, our complete binary trees have this, it's a fairly strict definition of it. You can actually tell me the shape of a complete binary tree if I tell you how many nodes there are. So for example, draw a tree, okay, draw a binary tree, draw a complete binary tree with 9 nodes. So there's only one answer to this. So pause the video here and draw this picture. Draw a complete binary tree with 9 nodes. Pause now. Okay, so hopefully you paused and hopefully you already drew this picture. See if you got this answer, okay? 9 node complete binary tree. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the only correct answer. Okay? Now, this level, there was one node. This level, there are two nodes. I have to have them all in before I can go to the next level. This level has 4. This level will be 8 when 8 nodes before we can start on the level after that. Before we add another level, we actually have to fill out this entire level completely. Okay, this is really important idea. So a binary heap is interesting in that we don't allow our trees to have a very, our shape is actually very defined. It's this complete binary tree idea. And it turns out that this idea, why it has to be complete, has a lot to do with how we're going to implement this thing too. So a complete binary tree is a binary tree where every single node on any one level that can exist has to exist before you start nodes at the next level, and you have to bring them into existence from left to right. Okay? So be careful about this. This is a shape. So this part, so the first part of this definition of a binary heap, this has to do with the shape of the data structure. Okay, so complete binary tree talks only about shape. It doesn't care about where the numbers go. They're just talking about the shape here. The shape of a binary heap is that of a complete binary tree. The heap order property, on the other hand, is what tells us where things go. So heap order property is heap order property. Okay, heap order, or so heap order property, some books just say heap order. What does heap order mean? So heap order is actually very simple. Parent has higher priority than child. Okay, so the heap order is simply the parent, the thing that's in the parent node has a higher priority than the children node. Now, it does not say which child is higher priority. It only says that the parent is higher priority. Okay, so for example, if I drew a couple of binary heaps here, okay, remember, so very quick note, remember that we are using the following: smaller value, higher priority. And this will result in what we call a min heap. So when we talk about min heap, this is what we mean. Smaller is higher priority. That's a min heap. We can also create max heaps. Max heaps are the opposite. Bigger value, higher priority. How do you know? Look at the root. Is it bigger than everything else or smaller than everything else? Then you know, okay? So in any case, if the smaller value has higher priority and what we get is a min heap, then what does this actually imply with heap order and so on? So for example, 1, 5, 10, this is a min heap. Okay, this is a min heap. It's a heap. Okay, heap order is maintained. Okay, heap order is maintained. Okay, now, really important idea for heap order is this. Okay, so this maintains heap order, sure. But not only does it maintain heap order, but this particular thing, oops, um, this particular object, it maintains heap order, sure, but it's actually more than just this. Okay, so something else to keep in mind for heap order is the following. Let's say that I added another value here. Okay. Now, first of all, actually, I'm going to add 2 values. So first of all, what you will notice, so this is also a proper heap. This is a proper heap also. Now, really important, because we're going to be talking about trees a lot. It's really important to distinguish the idea between heaps and binary search trees, which we haven't covered yet. But some of you may have met binary search trees when you were in high school or something like that, or as another data structure, you've heard of them. Um, Heaps are not binary search trees. They are not general purpose search structures. Really important idea. This is not for searching. The only thing you know about this heap is that the highest priority item is definitely at the root. You don't even know where the second item is going to be. You only know where the best one, the highest priority one is. So, first of all, if we look at priority, who is the highest priority item? Well, definitely one. That's the highest priority item, right? Who is the second highest priority item? Well, this is the second highest priority item right there. Where's the third highest priority item, though? It's actually not, first of all, it isn't at the 10. It doesn't have to be at the 10 because our heap order simply says parent higher priority than child. Parent is higher priority than child. Than children. That's all it says. It doesn't say that the first node has to be higher priority than the second node. That are so if they're siblings, so if they have the same parent, it doesn't say the left one is higher priority than the right one or the other way around. Okay, nor does it say that children of children can't be higher priority than a direct child. So for example, where's the third highest priority item in this heap? It's actually this 8. This is the third highest priority item in the heap, not the 10. Okay, so this can happen. So think about, maybe some of you have like, uncles and aunts that are younger than you. That can happen, right? Like if your parent was the absolute oldest child sometimes, and your grandparents had a kid really late as well. So like there can be like gaps, right? So this can happen. Okay, so parent has a higher priority than than its children. That is the only rule. Okay, doesn't say that the left child is higher priority than the right child. It does not say that that the nodes at one level is going to all be higher priority than nodes at the next. It only says parent higher priority than its children. Okay, that's it. Now, why is this important? Why do we care about this heap order so much? Because this is what makes this work fast. That's pretty much what it comes down to. Heap order allows us to implement this structure quickly. Heap order and its shape actually allows us to implement this structure quickly. Okay, so we're going to talk a lot more about that in later videos. This is it for now. So all you need to know about this from here is what is complete tree, what is heap order, and that's it. Okay, most important things. So in the next video, we'll talk about how do we create these heaps, how do we put things in, how do we take things out, and then we'll talk about implementation after that. Thanks, everyone.